In the last video, we looked at a simple recursive function that did not return anything. It counted down from whatever value it was given down to 0. Now we can modify that function so that it returns a value. So recursion is not limited to just void functions. You can return a value of any type. You can return ints, floats, doubles, characters, strings. You can also return objects. A string is an object too. So use the same technique. The outline is we have one or more cases where a value is returned computed by recursive calls. So these should be smaller problems that solve the same problem as the original problem, but they're smaller. And then usually one and possibly more cases where the value returned is computed without any recursion at all. That's considered the base case. So let's take a look at a simple example. Let's say we set up a function called add, and what it's supposed to do is it'll be passed in the value n, and it should compute the sum from 1 to n. So it's actually not that hard to do. So our base case would, once again, 0 is fine. So you say return, and in this case now you no longer have a void function. You want to return, let's say int, to keep it simple. Okay. So you change that, and I changed the name of it just so that it's sort of makes sense, and change the type that it returns to an int, and then when you return in the base case, you have to return. In this case, we just return 0. That's good enough. It'll work. And here's where you break it up into a smaller problem. So you say we keep a running total. So I'm going to break it up into steps. I'm going to say AR running total is equal to n, whatever that is, plus everything that you get from the add function for a smaller thing, a smaller problem. And we call add. Add is supposed to compute the sum from 1 to n. We call add with n minus 1, so it has to compute. This should, if everything works, should compute the sum from 1 to n minus 1. So it's smaller than the original problem, and then we just return this running total. Okay, and now you have to call add, and it returns a value, so let's store it. Result is equal to add 4. So if everything works, you should compute the sum from 1 to 4, which is 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. So this should return 10. So just print that out. Okay, there we go. Compile it. Let's hope there's no errors. If there are, we have to fix them. We're lucky. No errors. And we print out all the values. We go from 4 to 3 to 2 is 0, and the sum of all of these numbers is 10. So you might say, well, how did you do that without adding up all the values? We only add 2 things. It looks like we only add 2 things, but of course you know that since we call add recursively, when you call add recursively, you do the same addition with a smaller problem, and so on till you get to the base case. Sum from, and you don't have to go all the way to 0. We can say 1. If n is equal to 1, we just return 1. The sum from 1 to 1 is just 1. Right. So let's make that a tiny bit better. Okay, so it's a little bit more. It's probably a little better. You don't have to go to 0. It doesn't make a difference if you add 0 to 10. You just still get 10. Now we can make this smaller. We don't really have to print out the value of n. And also notice that we only compute a running total and then immediately return it. So we really don't need this. So I did it in steps just to show you what the steps were, but you really don't need all of that, and you don't need this variable either. And you can just return n plus add n minus 1. Okay, so I broke it down into steps before. I saved the value of whatever this was plus n, and then return that, but you don't need to do that. So this will work the same way. So once you get used to recursion, you can make all kinds of simplifications. Here you can just say the sum is from 1 to 4 is 10. If you ask it to compute the sum from 1 to 5, it will return a new value, which should be 5 greater, which should be 15. Oops, let's save it, compile it, and run it, and we get sum is 15. If you do 100, we should be able to do that. And you can, there's a formula for this, which is n times whatever n is 100 in this case, 100 times n times n plus 1 divided by 2. So it should give us 50 times let's see, n 100 times 101 divided by 2 is 50 times 101. That should be 5050, I believe. So you should be able to predict what your program should do, and sure enough, there it is, 5050. Okay. So you can set up recursive functions that return a value. You're not limited to void functions. The book uses example of a power function. So this is just like math.power or math.pow. In the Java in the Java library, there's a math.power function. And what it does is return raise whatever value whatever first argument you send in, it'll raise it to the power of the second argument. So x raised to the power y. So in this case, x is 2, y is 3, 2 raised to the power 3 is 8. So it should take 2 double arguments and return a double value. So let's write this recursively the way you would do it. And in this case, we're going to use ints. We're going to take a shortcut. Doubles are going to be a lot harder to do. So ints are definitely doable. So if you want to raise something to the power 0, that would be one of the base cases. You don't have to really do anything, but if it's less than 0, we can't do that. Let's just assume that our power function cannot raise anything to the power, anything to a negative power. In general, that is possible, but of course we just don't want to do it. So we can print out a legal argument and exit. So this exit will get you out of the program completely. So we're going to say that n is always going to be greater than 0. So the only other possibility, if it's not less than 0, if it's less than 0, we exit. So at this point, it's definitely not less than 0. It's 0 or positive. If it's positive, what you do is you find the power of x to a smaller value, that is n minus 1, is 1 smaller, and then you multiply that by x. So whatever this is, this whole thing is x raised to the power n minus 1, and then if you multiply it by x, you get x raised to the power n. So we're taking a big problem that is x raised to the power n, breaking it up into 2 pieces. One piece is very similar to the original problem but smaller, that is smaller by 1. And then you multiply it with x to get the whole result. Sort of very similar to the add function we just set up. And then here's our base case. In this case, the base case appears at the end. The base case doesn't have to be always at the top. This is not really a base case. This is just a situation where you're saying, well, we can't really handle negative powers. And so the base case is really over here. And I guess you could say this is part of the base case too, but this is something we're saying we cannot do right now. Okay. So if you call 2 raised to the power 0, it should return 1. How do you get 1? Because of this thing. The base case will return 1. Anything raised to the power 0 is 1. Mathematically, that's true. So that's why we're okay with doing this. If you raise 2 to the power 1, it will call power to 0 times 2. Power to 2 to the power 0 is 1, and 1 times 2 is 2, and so it should return 2. That makes sense. 2 to the power 1, it's just 2. And so on. You can see you have this outer call, and then you have these, the book calls them inner calls. That is, you inside this power function, this recursive function, you call power again, and inside that you call power again, and so on. Eventually you hit the base case, which is 1. Recursion stops, and we say that the recursion unwinds or is returned back up the stack, and you compute all of these things. Okay, and you can visualize this way. That is, you start over here, you can say power 2 to 3. This is like putting something on the stack. That's the general idea. This computes 2 to the power 2 and multiplies it by 2. Well, 2 to the power 2 is just 2 to the power 1 times 2. And 2 to the power 1 is just 2 to the power 0 times 2. 2 to the power 0 is the base case. You get 1. So then you compute 1 goes back here, times 2 is 2. Goes here. 2 times 2 is 4. Goes here. 4 times 2 is 8. And that goes here. And that's the final result. 2 to the power 3 is 8. Okay, so how do you start to think recursively? Now that is a skill that takes a long time, or just the right kind of approach to thinking about recursion. And when you think recursively, you do want to actually ignore some of the details. Even though you might have figured out how the stack works, forget about it. And then forget about all the in-between suspended computations that are happening and sort of temporarily finished or partly finished. So you do want to think about recursion as an abstraction and encapsulation principle. And you let the computer do the bookkeeping. You just want to think about the big picture. You want to think about how to break up a problem into smaller pieces and then eventually get a small enough piece that you can do using the base case. So consider this power function again. So this is how you think about the definition of power. If you're raising x to the power n, that's the same as computing x to the power n minus 1 and multiplying by x. So just ensure that you have the formula correct, and then ensure that the base case will be met. The base case in this case will be when n is 0. We're not going to consider negative values, and we are assuming that n is positive or 0 originally. Okay, so this will only work if that assumption holds. And if that assumption holds, when we get down to 0, we can solve the problem. X raised to the power 0 is just x. So that's not a problem. You don't really have to trace the entire recursive sequence. You just need to check 3 things. Make sure you do not have infinite recursion or runaway recursion, so that if you had runaway recursion, your program would crash. So you want to avoid that. Then you want to have stopping cases or base cases. You want those to return the correct values, and then you want the recursive cases also to return the correct values. So you want to think about these 3 things inside your recursive function. You want to check this power function against these 3 properties. Make sure there's no infinite recursion. The second argument will decrease by 1. That the n will go to n minus 1. Eventually, you should get a base case of 0. Actually, it should be 0. And then the stopping case, make sure that it returns the correct value. Anything raised to the power 0 should be 1. Okay, so power x to the 0 is the base case. It should return 1. That's the correct value for anything raised to the power 0. Make sure the recursive calls are correct. For if n is greater than 1, that is, you don't have the base case, power of x to the power n should return. This formula should be right. X to the power n minus 1 times x is actually x to the power n. So then you plug in the values and you have the right value, and you should be okay. That's how you check. Next up, we'll take a quick look at what's called binary search.